Section 5.1 talks about proofs by contrapositive or contrapositive proofs. So before we get into that, let's go ahead and kind of think about these different types of statements that we've seen before, and we'll remember what their special names are. So I'm going to sort of think of this P implies Q as my base statement, and I'm going to compare everything to that. So if you switch the order there, if you have Q implies P instead, that's called the converse. And we've seen that this is not logically equivalent. To P implies Q. So this is different than P implies Q. It could be true that P implies Q is true and Q implies P is false. They might be true at the same time, right? If they're both true, then that's when you get that if and only if. But that is the converse, and that is not the same as P implies Q. But we've seen that if you switch the order and negate them, and so that you get not Q implies not P, that is logically equivalent. So that's called the contrapositive. And this is logically equivalent to P implies Q. Right, so these two statements have the same truth values. So if I need to prove P implies Q, instead I could just prove not Q implies not P, because it's going to be true at exactly the same time. And when we do that, that's called proof by contrapositive. The last sort of way that we can organize these is I can either take the contrapositive and take its converse, or I can take the converse and take its contrapositive. Right, we end up in the same place. So we can think of this as either the converse of the contrapositive or the contrapositive of the converse. Since it's the contrapositive of the converse, it has the same truth value as the converse. And sometimes people call this the inverse, although that's going to be the term that we see least commonly. So the big things that we should know are the converse, which is not the same as the original statement, and the contrapositive, which is logically equivalent to that original statement. So then how does a proof by contrapositive work? So we're trying to show some statement of the form P implies Q, some conditional statement, that this is logically equivalent to its contrapositive, not Q, implies not P. So what we're really going to do here is we're going to do a direct proof on that contrapositive. That's what a proof by contrapositive is. It's when you do that direct proof, but on that contrapositive. So I'm going to assume the if of that contrapositive. I'm going to assume not Q. And then I'm going to do some stuff, use my definitions, use some algebra maybe. And at the end, I'm going to conclude my not P. And if I've done that, then I've concluded my proof by contrapositive. So let's see some proofs in action. So the statement I want to prove here is, suppose we have an integer x. We want to show that if 7x plus 9 is even, then x is odd. So let's first just do a direct regular old proof. So I'm going to assume my if. So we'll say assume or suppose that 7x plus 9 is even. Then by definition, 7x plus 9 can be written as 2m for some integer m. Now, what can I say from there? I'm trying to get to the fact that x is odd. So what I want to do is probably try to solve this expression for x. So we can say adding 9. Oops, I guess I don't want to add 9. I want to subtract 9. Let's fix that. Subtracting 9 from both sides gives 7x equals 2m minus 9. But now if I try to divide by 7, I'm going to end up with non-integers, right? So we have to be careful here with how we're going to do that. So we ask ourselves sort of, where can we go from here? I know that I want to try to show that x is 2 times something plus 1, because that's going to allow me to say that it's odd. So I'm allowed to push even things. I'm allowed to push things that I know their sign over to the other side. So what I can actually do here is I can actually subtract 6x as well. So let's see what that's going to look like. So subtracting 6x gives, now I do have my x, and that's equal to 2m minus 6x. And let me go ahead and split up this 9 into a minus 10 plus 1, because that way I'm going to have that plus 1 that I want for my odd definition. And now we can say, so x is equal to 2 times m minus 3x minus 5 plus 1. So this is sort of weird because I've written x in terms of itself, but because it is an integer, this will still be an integer. So I have that x is 2 times some integer plus 1. So then x is odd. Right, so that was our direct proof. That works, but it's kind of a little sketchy. So let's see if we can rewrite that using proof by contrapositive and see if it works nicer. So for contrapositive, we're going to assume the negation of the consequent here. So I'm going to assume x is even. All right, so maybe we'll want to start telling the reader what we'll do. So we'll proceed by contradiction, maybe, just to kind of let the reader know what's going to happen here so they're not surprised when we start assuming x is even. So I assume x is even, then x is equal to some 2m for m in z. So 7x plus 9 is equal to 7 times 2m plus 9. I'm trying to show the opposite of 7x plus 9 is even. So I'm trying to show that this is odd. So let's see if we can get it in that odd form. So I'm going to have 14m plus, I know I want to have a plus 1, so I'll say plus 8 plus 1. So then I can get 2 times 7m plus 4 plus 1, where 7m plus 4 is an integer. Thus, I can conclude that 7x plus 9 is odd. Right? That proof went much more clearly. I didn't have to do this weird thing where I defined x in terms of x. It all just sort of worked out nicer for us, and that's the power of the proof by contradiction in this case. Right? So I assumed the negation of my consequence there. I concluded the negation of my hypothesis, and that is what I want. So here's a proof for you to try. I want you to see if you can prove the following proposition. So suppose x is an integer. I want you to show if x squared minus 6x plus 5 is even, then x is odd. So again, go write out a nice formal proof, and I want you to try to use contrapositive. And in particular, it might be important to think, what would happen if I tried to do this not using contrapositive? What issues would I run into and why? So why is contrapositive better in this case? So let's do one more proof by contradiction here. So we want to suppose that x and y are integers, and we want to show that if 5 does not divide x times y, then 5 doesn't divide x, and 5 does not divide y. So just remember the symbol here means does not divide. So it's the negation of that divide symbol that we saw before. Okay, so let's think about how we would prove this. So it's really hard to assume that 5 does not divide something. Because, like, what does it mean that it doesn't divide, right? It means there doesn't exist an integer so that, x times y equals 5 times something. But proving something does not exist is much harder to do to prove than proving something does exist when you're trying to do it in general, for general integers. So here, when we're doing proof by contrapositive, it's going to allow us to assume the negation instead, right? So I'm going to assume the negation of my consequence. I'm going to prove the negation of my hypothesis. And for us, the negation of those negations are going to bring us back to divides. And it's a lot easier to prove things about divides than it is does not divide. So that's a good clue that I want to assume these negations instead. But again, remember, we have to switch the order when we do that proof by contrapositive. So let's go ahead and do that out. So again, we'll let the reader know that we're going to use contrapositive. So we'll say we'll proceed via contrapositive. So we'll assume the negation of my consequence. Now be careful here, we have an and, so we have to negate that and as well. So we'll assume that 5 divides x. The negation of that and is or 5 divides y. Right? So it's not true that 5 doesn't divide x and 5 doesn't divide y. So either 5 divides x or 5 divides y or both. This divide symbol should be a little bit more straight up and down, so let's fix that. Now that I'm assuming this is true or this is true, because there's 2 different options, that's a good clue that I might want to do proof by cases. So we'll say case 1. Let 5 divide x. Then, since 5 divides x, that means x is equal to 5 times a for some a in the set of integers. Or the set of natural numbers, depends on how we're defining things. But because we said that x was an integer, we need to allow for positive and negative. So we'll have a be that integer as well. Now, what I was trying to prove is the negation of this 5 does not divide xy, which is 5 divides x times y. So let's think about what x times y is. So we'll get, x times y is equal to 5a times y, which is equal to 5 times ay, where ay is an integer. Thus, x times y can be written as 5 times an integer. So 5 divides x times y as needed. Now, my next case, 5 divides y, that's going to look a lot like the 5 divides x case. So this might be a case where you would want to use without loss of generality. But it is a little bit different because we had these x's and y's, so I'm just going to go ahead and actually write out that specific second case as well. But I think this would be totally fine if you wanted to use that without loss of generality here. So in my second case, let's say 5 divides y, then it's really going to just follow through the same thing. Y equals 5a for some integer a. So xy equals 5 times a, that's my y. I'll put the x out front, which is equal to 5 times xa, where xa is an integer. Again, here we're using this fact that the integers are closed under multiplication. So if x is an integer and a is an integer, then so is their product. Thus, 5 divides x times y, again, which is what we wanted to show. So then we can say, in either case, when 5 divides x or 5 divides y, we get that 5 divides x times y. So we're done. You could say, therefore by contrapositive, if 5 does not divide x, then 5 does not divide x and 5 does not divide y. So let's do that. Thus, by contrapositive, I like to really make sure it's clear what we're doing right at the end of the proof. If 5 does not divide x times y, then 5 does not divide x, and 5 does not divide y, right? Because, again, let's think about why this logic works. If it was true that either of these was true, so if either 5 divided x or 5 divided y, then it must be the case that 5 divides the product. That's what we showed up here. If either 5 divide x or 5 divide y, it has to be true that 5 divides x times y. But since it is not the case that 5 divides x times y, then it can't possibly be the case that either of these were true. Otherwise, we would sort of break math, because we know if 5 divides x or if 5 divides y, 5 has to divide the product. So if it doesn't divide the product, it can't divide either one. Right? So that's how that logic in that contrapositive is working. So I encourage you to think through that some more.